Have you ever looked at a university physics exam and just felt your brain immediately shut down, like you're trying to read some ancient alien text? Yeah, you are not alone. So today, we're going to take a real exam and pull it apart, not to grind through the math, but to find the really cool fundamental ideas that are hiding inside. And here it is. This is an actual midterm from an electromagnetic theory course. I mean, just look at it. All those equations, the symbols, the point deductions for every little mistake. It's totally designed to be intimidating. But we're going to look right past all that, because behind every single one of these problems is a core concept about how our universe actually works.
And that's the whole point of this explainer. We are going to completely, 100% ignore the nasty calculations. Instead, we're going to focus on the logic, the story that each problem is telling us about the laws of physics.
So here's our game plan. We've got 4 big ideas to unpack. First, we'll dive into a physics challenge about these things called eddy currents. Then we'll see how physicists use a super elegant shortcut to solve a problem about mutual inductance. After that, and this one is wild, we're going to uncover a surprising secret about how energy actually moves, using something called Poynting's vector. And we'll wrap it all up by looking at the fundamental rules of waves and polarization that define what light even is.
Okay, first up, problem 1, eddy currents. This whole problem is framed around spinning spheres, which is a great way to help us visualize the unseen forces that get generated.
So the whole question really just boils down to this. Picture it. You've got a solid metal ball and you start spinning it inside a magnetic field. You know, like between the north and south poles of 2 big magnets. What in the world happens inside that piece of metal? Well, the answer is you get these things called eddy currents. You can think of them like little whirlpools or eddies of electrical current that start swirling around inside the ball. They pop into existence simply because the metal is moving through that magnetic field, and that motion literally shoves the electrons around and gets them flowing. So how does that actually work, step by step? Well, this slide breaks it down perfectly. It's really a 3-part story. First, the spinning motion creates a force on all the free charges inside the metal. Second, that force starts to push the charges apart, which creates its own little internal electric field. And finally, the whole system settles into what we call a steady state, where the electrons find a nice, constant path to flow in. So motion creates force, force creates separation, and that leads to a steady current. That's the logic. All right, let's jump to the next problem. This one is all about something called mutual inductance, but really, it's a lesson in how to think like a physicist. How to find the beautiful, elegant shortcut. So what is mutual inductance? In simple terms, it's just a number that tells you how much the magnetic field from one coil of wire influences another coil of wire nearby. But here is the magic trick, the absolute key to the whole problem. The effect is perfectly symmetrical. The way coil 1 affects coil 2 is exactly the same as the way coil 2 affects coil 1. This symmetry is everything. And this slide just shows you why that symmetry is so brilliant. The problem asks you to figure out the effect of a small, little coil on a huge, infinitely long one. Now, calculating the magnetic field from a short, finite coil is a total mathematical nightmare. It's messy and complicated. But because of that symmetry we just talked about, you can just flip the problem on its head. You can pretend the current is in the big, infinite coil instead. Its magnetic field is perfectly uniform and incredibly easy to calculate. And because M12 equals M21, you get the exact same answer with like 1/10 of the work. It's just a gorgeous example of using a deep physical principle to dodge a ton of painful math. Okay, I gotta admit, this next one is my absolute favorite. Problem 3 introduces something called the Poynting vector, and it makes us ask a really, really weird question. Where does the energy that powers our stuff actually come from? Seriously, think about it. When you plug in a lamp, you've got a wire running from the wall to the bulb. We all assume the energy travels down the wire, right? Like water flowing through a pipe. We picture electrons marching along, carrying little backpacks of energy from the power source to the light bulb. But is that what's really happening? Well, this is where the Poynting vector comes in. This vector, which we call S, is something you calculate using the electric and magnetic fields that exist in the empty space around the wire. And what it does is it points in the exact direction that energy is flowing. It's like a tiny little weather vane, but instead of wind, it shows you the flow of energy. And here it is, the mind-blowing secret of electromagnetism. When you actually calculate the pointing vector for a wire powering a light bulb, you find it does not point down the length of the wire. It points from the space around the wire directly into the wire all along its length. The energy is actually carried in the electromagnetic fields that fill the space around the conductor. It flows in from the sides where it gets turned into heat and light. The electrons in the wire, they're just helping guide the process. The fields are doing all the heavy lifting. Yeah, I know, it's wild. All right, the last two problems on the exam are a little more abstract, but they get right to the very heart of what light and all electromagnetic waves really are. They're about the fundamental rules of the road. So question 4 basically asks, what's the universal recipe for a wave? What's the mathematical signature that tells you something is a wave? The key insight is that any function, I don't care what its shape is, describes a traveling wave as long as it's built around this very specific combination of position and time you see here. If a function follows that rule, it means it describes some shape that just moves through space at a constant speed without falling apart. It's the universal calling card of a wave. Now for the final question. This is a fantastic what-if thought experiment. We all learn that light waves are transverse, right? The electric field wiggles up and down or side to side, but always perpendicular to the direction the light is actually traveling. Why? Well, it turns out that rule comes directly from one of Maxwell's equations, specifically Gauss's law, which says the divergence of E is 0 in empty space. But then the problem says, okay, but what if the law was different? What if it looked like this hypothetical equation instead? And it turns out, under this new fake law, light could wiggle in the same direction it travels. It's an amazing way to show how one single simple-looking equation fundamentally dictates the nature of light itself. So there you have it. We've made it all the way through a university physics exam without solving a single integral. Now, let's just take a step back and recap the big ideas we've managed to unlock by looking past the math. We've really unlocked 4 huge concepts. First, from eddy currents, we learn a simple truth. Motion through a magnetic field creates forces and gets charges moving. From mutual inductance, we saw that symmetry isn't just pretty, it can be a physicist's best shortcut. From the pointing vector, we learned the mind-bending fact that energy flows through the fields around the wire, not through it. And finally, we saw how just a few fundamental laws are responsible for defining the entire nature of light and waves. And the thing is, these aren't just clever answers to get you a good grade on an exam. These are the literal rules of our universe. These principles explain how your electric motor works, how a power generator works, how radio antennas broadcast signals across the planet, and how light interacts with basically everything you see. They are the invisible architecture of our modern world. So the real question is, now that you can see the ideas hiding behind the equations, what else around you starts to make just a little bit more sense?